Hi, my name is Tobias Olsson and I will be presenting our paper Optimized Dependency Weights in Source Code Clustering. My co-authors are Morgan Eriksson, Anna Winkvist, and we are all from the Department of Computer Science and Media Technology at the Linnaeus University. Source code clustering uses the information found in the source code. It relies on the fact that developers have organized the code into groups of well-defined responsibility and try to isolate such groups from each other. At the architecture level, such groups are often called layers, subsystems, or modules. We will be using modules in this presentation. We can, for example, think about dependencies between classes and trying to find the parts that are highly dependent on each other, or we can also use semantic information, that is, words that are similar or have a similar meaning, to find these such groups. Clustering can be used to perform architectural recovery, where the architectural information has been lost or is not up to date. So we try to automatically discover such suitable modules by clustering the source code. In our case, we are working with architecture conformance checking, and we are using reflection modeling. And one part of reflection modeling is that we need a mapping between the module and the source code. For a large system, such a mapping is hard to create manually, so it would be good to create such a mapping automatically. Then we can use incremental source code clustering or orphan adoption. One such algorithm is the human-guided clustering method and its attraction function CountAttract that uses the dependencies of the source code to find a suitable module for a new source code entity. In this simple example, we have two modules, graphical user interface and logic. We have a new source code entity called string change that should be automatically mapped to one of these modules. Just counting the dependencies, we can see that it would be beneficial to put string change into logic. So, the problem of automated mapping is a little bit more complicated. We can have different types of dependencies. We can also have these allowed module dependencies as specified by a software architecture. In this example, entities mapped to the graphical user interface module are allowed to depend on entities in the logic module. The entity under consideration can also have dependencies to other entities that are not already clustered, making things complicated, and this may also affect the automatic mapping procedure. HugMe and CountAttract can use the weights of the dependencies, and also the allowed module dependencies and the order of the clustering can be controlled using two algorithm parameters. In this work, we focus on the weights of different dependency types and its effect on the algorithm performance. We investigated three different weighting schemas. The simplest form of schema is just to use uniform weights, and that's a reasonable choice if we can assume low coupling and high cohesion. Another choice would be to take a look at the source code and try to understand how many of the dependencies are internal to modules and how many are external. If we know the ground truth mappings, we can compute this by dividing all of the internal dependencies of a certain type with all of the module dependencies of this type. So if we get 1.0, all dependencies are internal. That is, we have a high cohesion and low coupling design for that type of dependency. However, we also believe that the dependencies and the types of dependencies interconnect, and it's more complicated than just looking at one single type at a time. So we opted to use a genetic algorithm and the ground truths to find the best weights. And of course, this is quite hard to calculate and take some time. We then proceed to compare the F1 score of the precision and recall of the CountAttract function and see which of these weighting schemas perform best. We do this for 8 subject systems where we have the intended architecture to ground truth mappings as defined by experts, and this has been the work of the ECSA2021 workshop for a few years. So what does the related work say about different weights for dependencies? We have mainly found research in the software architecture reconstruction area, and in general they seem to value method and function calls dependency high, and inheritance and realization dependencies low. One weakness we have found in the related work is that they don't really use any ground truths as defined by experts when they evaluate the different clusterings. So basically we can know that different weights will give different architectures, but we don't know if one of the clusterings is actually better than the other. Another approach has been to use all of the dependencies as a baseline, as a ground truth, and then try to find what types are needed to reconstruct this baseline. In this case, it's likely that the most frequent type will highly affect or dominate the clustering. For our genetic algorithm, we define each weight as a gene, and an individual is then a complete set of weights. We use 30 individuals in a generation, and we calculate the fitness for an individual using 10 initial sets. The size and composition of the initial set highly affects the performance of the algorithm, so we use the same 10 initial sets for the whole generation. We calculate the F1 score for each individual and each set, and we say that one individual is more fit than another if it has a higher F1 score in a majority of these 10 initial sets. We generate a new individual by using a tournament selection process. That is, we select a subset of the generation and take the 2 individuals with the highest fitness from that subset. Then we use uniform crossover to select what genes should be taken from what parent. There is also a chance of random mutation, and in that case one random gene will be slightly offset. There is also elitism, that is, the most fit individual from one generation will survive to the next, but this is also capped with a threshold so that an individual does not survive for too long. This is to avoid getting stuck in local optima. We executed this algorithm for 300 generations for each of the system. After that, we didn't really see any improvement in the F1 score or real changes in the weights. This means that we have 720,000 mappings done in total to compute the optimized weights. So in this table you can see the optimized weights as highlighted in yellow and italics, and the internal coupling ratio computed. We can see that 2 of the systems are generally not built using the low coupling high cohesion principle. This is Ant and Teammates. Overall, the dependencies are not that cohesive. That is, it's more likely almost that a dependency is external to the module than internal. However, for both of these systems we can find some dependency types that are actually very cohesive. For example, the extends and implements dependencies in Ant and the extends dependency type in Teammates. We also have the same for this physical file structure when files are located in the same directory. In general, we see that the optimized weights are 0 for all of the system for the method called dependency type. This is in contrast to the related work. Inheritance also seems to have high value in many of the systems. Pro-M is kind of like a little bit of an exception here because it's very well organized physically, so the physical structure of files is highly relevant, so none of the other dependency types are really needed to successfully cluster Pro-M. The file relations also seem generally quite important. We have possibly some specific design strategies for error handling and constructor calls to use exceptions and maybe factory patterns for special types of systems. We can see that the constructor calls are highly valued in some of the systems, and also the throws exception handling is valuable in some of the systems. So now that we have our weights for the dependencies for our 3 dependency schemas, so we devise an experiment to see which of the weighting schemas are best. For this we do 50,000 mappings for each of the system and weighting. This is to cover a large portion of the initial sets regarding their random composition and size. We also have the random hugme parameters that control the order of the clustering and also how allowed module dependencies should be treated. We use our tool that's available on GitHub, and we execute the experiments on our high performance computing cloud. All in all, we do 1.2 million mappings. Then we use some filtering to remove strange parameter values for the control of the order of clustering and the allowed module dependencies. This is to mimic an expert using setting these parameters to some good values. And we have 578,137 mappings left in our dataset. The results show that the optimized weights have significantly higher F1 score in all of the systems. The difference of the median effort score versus the intuitive weights are 0.13, and the difference between the optimized weights and the uniform weights are 0.17. This is quite a large difference, so we think this is highly significant. The intuitive weights are a little bit better than the uniform weights, but not by very much. So it is doubtful that using kind of like this intuitive weights are better than actually just using uniform weights. Maybe just remove the method calls and set these to 0, and you would have perfectly good results from the uniform weights also. Looking at one of these systems that have not been overall designed using low coupling high cohesion, we can see that the optimized weights in green are almost twice as good as the intuitive weights if we have a large initial set. And overall the difference in performance is larger in these two systems, where a few of the dependency types are actually cohesive. If we look at a system that overall has been designed using low coupling and high cohesion, the difference of performance is much smaller, but still the optimized weights in green are generally better than the other two weighting schemas. One interesting effect is also that uniform weights can be better than intuitive weights when the initial set is very small. This is because the uniform weights, this schema has much more weights to work with when the initial set is small, and can thus make the algorithm actually perform a little bit better in these cases. In the future, we think that doing more comparative studies to investigate the difference in the results for the method call dependency type would be interesting. We could run different software architecture recovery clustering algorithms on our ground truth systems and see if this can be repeated. We can also try some systems that are not that well organized from a physical structure point of view. One large problem is, of course, that if we have a new system or if we want to use this practically, we don't have a ground truth. So how can we derive these weights from the initial set? How large does this initial set have to be? Is it viable to execute a genetic algorithm on a small initial set? Some interesting ideas we have is that maybe negative weights can be useful in clusterings. And we have basically investigated one set of module weights for each system. You could also have optimized module weights for each pair of modules. This could also be an interesting approach to further increase the performance of HugMe and Countertract. However, in this case, there will be a large amount of weights to compute, and this will be a challenge. Thank you for listening, and feel free to check out the replication package. There you can check the genetic algorithm implementation and things like that. And I'm ready for some questions. Thank you.